All right, so page 16, I asked you guys to answer questions 1 through 3. Let's go ahead and go through questions 1 and 2. The information that you need to answer all 3 of these questions is on page 15. What's the population here? All the power forwards in the NBA. What's the sample? 5 power forwards, the 5 selected power forwards specifically. What is the shape of the distribution? That was on page 15. On page 15? Looks approximately normal to me. If you look at page 15, it is approximately normal. What's the mean? 80.087. And that would be mu, because that is my population mean. What's the standard deviation? 1.519, and that would be my sigma, because that is the population standard deviation. So far, so good? Number 3, I asked you to take a random sample of 5 power forwards. I wanted you to write down their heights and then find the mean of that sample. And I wanted you to do that 3 times total. So I have done that. I've got my 3 means up on the board. I want you guys to come up and add your dots. Once you have your 3 samples of 5 power forwards picked out, calculate the mean for that sample, and then you're going to come up and put a dot on the board. All right. So, if I asked you to describe this shape to me, what is this shape? Well, my big bump of data is right here, right? It kind of comes down like this. It's got a little bit of a tail over there, but not a lot of a tail, right? It actually comes down a little bit quicker. Here it comes down and then out. Does it look like it's skewed? Not really. Does it have more than one big bump? No, so I wouldn't say that it's bimodal, it's unimodal. I think it's very approximate, very rough here. But I think if we did more samples or we had more people that were doing samples, it would begin to take on more and more of an approximately normal shape. This is approximately normal. I know ours doesn't look exactly approximately normal. But honestly, when we're doing these sampling distributions, approximately normal means I'm unimodal. It doesn't have a really strong left skew or a really strong right skew. This is my sampling distribution of X bar. Why X bar and not P hat? We're not doing proportions, we're not doing percentages, right? We found means, we found averages. We found averages of samples, that's why it's an X bar. If I asked you to ballpark what the mean was on here, looks like it's about what? Looks like it's right about 80, right? Maybe a little bit bigger. I'm okay to write down 80. Standard deviation. What do you think our standard deviation is? So one standard deviation on either side, when we're approximately normal, should grab like 68% of the data. So it should grab more than half of the data, but not really 3/4 of the data. So where would you put the cutoff where you think we'd grab something between 50 and 75% of these dots? What'd you say? 0.6 away, so 3 marks over. Let me see where that would put us. right here to right here. Do you feel like that captures a good chunk of the data? Probably somewhere around 70-ish% of the dots. Okay, I'm all right with using that, 0.06. Oh, I'm gonna go ahead and leave. No, I want those off of there. We'll just draw it. Oops. Oh my goodness. Just trying to draw on the board. So something like this. Okay. So let me write down what we said again. We said the mean was about 80. The standard deviation estimated was about 0.06. What did we say the population mean was? 80.087. That was about where we just ballparked it visually from our sampling distribution. The mean of our sampling distribution, that's what mu x bar means, is going to be the same as the mean of the population. And while we didn't calculate it out to the 0.87 part, we were told that on page 15, that that was the mean of the population. I knew ahead of time that our sampling distribution, especially if we had more and more and more dots on there, was going to come out to be approximately normal, because the population distribution is approximately normal. If the population distribution is approximately normal, the sampling distribution will be approximately normal. What was the standard deviation for the population? 1.59 or 1.519. Oh wait, it wasn't 0.06, it was 0.6 because we went 3 spaces out. Sorry guys, I wrote the wrong thing down. To find the standard deviation of a sampling distribution for x bar, we take the population standard deviation and we divide it by the square root of n. So this time I'm dividing it by the square root of 5 because why? Yep, you picked out 5 people in your sample each time. So n is 5. So the sampling distribution standard deviation is 0.67. Did we do a pretty decent job of getting close to that just eyeballing our graph? Absolutely. I want you guys to use a normal distribution to find the probability of taking a random sample of 5 power forwards, like we just did, and getting a sample mean less than 79 inches. So what I want you to calculate is the probability that x bar is less than 79. Take about 2.5 minutes to do that. What's the first thing you should do on number 6 before you grab your calculator, before you do anything else? Draw a picture. And your picture should look like a normal distribution. So you should have a normal distribution curve. You need to have your mean in the center. We know the mean because it's the same as my population mean, so 80.087 goes in the center. Standard deviation of 0.67 needs to be labeled. We need that capital N. We need the mean and the standard deviation labeled. There we go. We need to have our X value on there. What are we finding? Sample mean of 79 inches or less. So I put 79 on. Has to be on the left side because it's smaller than 80. And then we shaded to the left because we wanted less than. Less than is left. All right, so after you have your beautiful artwork up, what are you going to do? Normal CDF. Numbers that need to go in your parentheses for normal CDF. Negative 1,000, 79, 80.087, 0.67. You did negative 1,000, I used 0, it's fine. So when you're picking your lower bound and upper bound, like whichever one you have to be finding, it's okay to look at the situation. Like we're talking about heights of power forwards. Nobody's going to be 0 inches tall, so that's why I went ahead and picked 0. But negative 10,000, negative 1,000 is perfectly fine as well. You want to make sure that you're at least as far out as that distribution could possibly go. The upper bound was set for us at 79. What'd you guys get when you popped it in the calculator? There we go. 0.0524. All right. How did we know that this one was approximately normal other than it said use a normal distribution? How did we know that we could use a normal distribution before they even said it? What'd you say? 10% condition allows me to use my standard deviation formula. What was it that we were checking for populations? We did large counts. Can't do large counts on this. N times P, we don't have P. We don't have a percent. We don't have a proportion. Population distribution was approximately normal. That gives me a free pass. If the population distribution is approximately normal, the sampling distribution is guaranteed to be approximately normal. So if they tell me or if I have access to information that I can see what that population distribution is, then I can use a normal distribution to calculate my probabilities. The other thing that we can do, and I want you guys on page 17 to write this down. If the population is approximately normal, then the sampling distribution of X bar will be approximately normal. Or if N is greater than or equal to 30, then my sampling distribution will also be approximately normal. We call this the central limit theorem. Sampling distribution of X bar, the mean of X bar is going to be the same as the mean of the population. For our variability, sigma of X bar is going to be the standard deviation of my population divided by the square root of n, however big n is. We can get normality one of two ways. I know I just said this, but normality comes one of two ways. Either they tell me the population distribution is approximately normal, and then I don't have to check anything, or n has to be greater than or equal to 30. This is called the central limit theorem. And before we do the check your understanding, I want to show you guys kind of how the central limit theorem works and why we're looking at, like, why is it 30? Honestly, because a bunch of statisticians got together and they said if it's 30, it's going to be approximately normal. but I want to show you. So if you look at page 18, or sorry, it's page 19, my apologies. Page 19. There's another set of tables, only now instead of looking at the power forwards, we're looking at what? Shooting guards. What's that distribution look like? Left skewed, right? So we have a left skewed population. I'm going to show you the work that my students did last year for that activity. I had them pick out a sample of size 2 and a sample of size 10. And while they had trouble making dots on the screen nicely, when they had samples of size 2, this is what our distribution looked like. Notice it's still kind of skewed left. But as my sample size got bigger, what happened? Variability got smaller, and it took on more of an approximately normal shape, more where I was unimodal and not skewed off to one of those two sides. So the larger my sample size, the more approximately normal it's going to be. We've got this cutoff of 30. If we have 30 or more, we say central limit theorem tells me the distribution is going to be approximately normal. If the population is approximately normal, but my sample size is very small, I can still do that. Because if my population is approximately normal, the sampling distribution is automatically going to be approximately normal. If the if the population distribution is anything different, then I need a large sample size, 30 or more. I want you guys to try to check your understanding for today. Let's take we got 4 parts to it. Let's do about 4 minutes. That'll give us 4 minutes to go over the answers. Sorry there. You doing okay, Keen? Okay. What's the shape of the population distribution? Approximately normal. They said right here that it was approximately normal. So to do part A, we're going to do a normal distribution. Oops, sorry. Good grief. Mean is my population mean of 18.5. Standard deviation is my population standard deviation of 5.3. Because if I do 5.3 divided by the square root of 1, I get 5.3. So when it's for one person, it's just the population standard deviation, population mean. We want to find the probability that x is greater than 25. So normal CDF. 25 is my lower bound. I went with something enormous for my upper bound, 10,000. 18.5 for mu and 5.3 for sigma. I got 0.11. For part B, we're going to choose a simple random sample of 10, so n equals 10. Can I still use a normal distribution here? Because population is approximately normal, so we're going to get away with a normal distribution. What's the mean of the sampling distribution? 18.5, exactly the same as the population. Calculate and interpret the standard deviation and verify that the 10% condition is met. Is the 10% condition met? Because that has to be met for me to use the formula. How would you check it? Close. Yeah, 10% of all U.S. teens. I need where 10, my sample size, is less than 10% of my population, all the U.S. teens. So are there at least 100 U.S. teens? Then my 10% condition is met. Standard deviation, we do sigma divided by square root of n, so 5.3 divided by the square root of 10, so 1.676. Interpretation, the mean number of minutes, the average number of minutes spent watching YouTube in a sample of 10 U.S. teens typically varies by 1.676 minutes from the mean of 18.5 minutes. Find the probability that the mean amount of time spent watching YouTube for teens in the sample exceeds 25 minutes. Can I do a normal approximation? Yes, because population is population is normally distributed. 18.5 is my mean, but now my standard deviation is 1.676. So then we do normal CDF. This time, my notation changes a little bit. Now I don't want that x is greater than 25. Now I want x bar, the mean of the sample, is greater than 25. Normal CDF, 25, 10,000, 18.5. New standard deviation of 1.676. And I got something outrageously small, 0.00005. You might see this written on your calculators as 5 times 10 to the negative 5, or 5e negative 5. Couple things real quick before you guys leave. Homework's due on Tuesday. There's extra credit if you do number 4, because that's something that we haven't covered, but you should be able to do it if you want the extra credit for it based on what we did with proportions. So extra credit for number 4, 1 through 3 is due on Tuesday. Have a fantastic weekend, everybody.